This is a review of some of the basic derivative rules. First is the power rule. The derivative of any polynomial or something that looks like a polynomial, you just subtract 1 from the exponent and move that exponent to the front. So for example, if I want to take the derivative of x to the 3/2, I move this 3/2 to the front and turn it into a multiplication, and I subtract 1 from the 3/2, and it becomes x to the 1/2. Here's another example. I'm going to rewrite this as 2x to the 3rd minus 7x to the -4, because -4 is just easier to see. So when I take the derivative of this, f prime of x will be 6x squared. The 3 moves to the front, multiplies by the 2. And then minus, well, the -4 moves to the front, so it's actually going to be a plus now. 7 times 4, -7 times -4 is positive 28, x to the -5th. And you can rewrite that with the x to the 5th in the bottom, but it's not necessary. Product rule. You have two functions that are being multiplied together. You can take the derivative by taking the derivative of the first times the second plus the derivative of the second times the first. So if I take a look at this example, the derivative of the first is 3x squared times the second in its original format plus the derivative of the second, which is 6x minus 8, times the first in its original format. You can multiply it out, but you don't have to. Quotient rule. If you have the derivative of two functions that are divided by each other, you have the derivative of the top times the bottom minus the derivative of the bottom times the top, all over the bottom squared. You may hear this as low d high, low times the derivative of the high one, minus high d low, all over low squared. Low d high minus high d low over low squared. So you may see it either way. If I take the derivative of this, I'm going to take the derivative of the top, 4x minus 5, times the bottom in its original format, so low d high, minus high d low, or the derivative of the bottom, 3x squared, times whatever the top was in its original format, all over the bottom squared. Again, you do not need to simplify that at all. Chain rule. If you have a function inside of a function, you take the derivative of the outer function, leave the inner function exactly the way it was, then multiply it by the derivative of the inner function. So this is kind of like x to the 5th minus 2x on the inside of some function x to the 6th. Now, using x is probably not a great idea, but it's some function to the 6th power. So if I take the derivative of this, I'm going to do the exponent power rule. So 6 times whatever that inside function is, leaving that the same, to the 5th power. So that's the first part. That's taking the derivative of that outer function and leaving the inner part the same. Then I'm going to multiply it by the derivative of the inside, which is 5x to the 4th minus 2. Again, you do not have to simplify it. Additional derivatives to memorize. Sine's derivative is cosine. Cosine's derivative is negative sine. Tangent's derivative is secant squared. Cosecant's derivative is negative cosecant cotangent. Secant's derivative is secant tangent. Cotangent's derivative is negative cosecant squared. E to the x's derivative is e to the x, and natural log's derivative is 1 over x. And again, all of these things could have chain rules or product rules or anything like that, but you have to memorize these derivatives. So we're going to do some mixed practice. First one, if I take the derivative of x cubed is 3x squared. The derivative of 3 sine x would be 3 cosine x. Nothing really other than just something memorized and a power rule in that one. Number 2, if I take the derivative of this is going to be a product rule. So the derivative of the first is 6 times the second part in its original state, plus the derivative of the second one, which is 2x minus 4 over x. So the derivative of natural log is 1 over x, times 6x plus 5, which was just the first part in its original state. You do not have to simplify that. Number 3, you could treat this in a couple different ways. You can treat it like a quotient rule. So the derivative of the top is 0 times the bottom. 0 times anything is 0, so it doesn't matter. Minus the derivative of the bottom, which is just negative 6x, times the top. Notice that minus a negative is going to turn into a plus, all over the bottom squared. So if I realize what I have, it's just 6x over the bottom squared. Or I could rewrite this as 4 minus 3x squared to the negative 1 and treat it like a chain rule. So I could do it that way. So f prime of x is negative 1 times 4 minus 3x to the negative 2, or sorry, 3x squared. Four minus 3x squared to the negative 2. And then I have a chain rule, so I have to take the derivative of the inside, which is going to be negative 6x. And notice that if I simplify the minus and negative, multiply those together, it becomes positive. And then I can move this negative 2 power to the bottom. These two things are equivalent. Number 4, this is definitely something that has to be a product rule, or quotient rule until I rearrange it to be a product rule, but that's probably not even beneficial. So derivative of the top would be 6x squared times the bottom in its original state, minus the derivative of the bottom, which is cosine x, times the top in its original state, all over the bottom squared. And we'll leave that like that. Number 5 is a chain rule. 4 cosine of 2x to the third. So that's just taking the derivative of the outer shell. Oh no, come back. Times the derivative of the inside. The derivative of cosine is negative sine. Notice the inside stays the same. And then there's a third layer to this. So the outer layer was the 4th power. The middle layer is the cosine. The inner layer is the 2x. So the derivative of 2x is just 2. So if I simplify this, it would be negative 8 cosine of 2x to the third times sine of 2x. Notice I just add 2. I just move this negative to the front, and 4 times 2. Number 6, let y equals u v be the product of two functions u and v. So we want y prime of 2. So that's going to be u prime of 2 times v of 2 plus v prime of 2 times u of 2. So it's derivative of the first times second plus derivative of the second times first. So I'm just going to make some substitutions where everything goes. So this is 3, this is negative 4, this is 1, this is 2. So it's negative 4 plus 6, which is 2. Number 7, they give us some information about the function f, so we're going to find g prime of 4. So g prime of x, in this case, this is going to be a product rule. So I'm going to take the derivative of squared x, which is, remember that the squared x is x to the 1/2. So that's 1/2 x to the negative 1/2. Just taking the derivative of that using the power rule. Times f of x So this is going to be a product rule. So derivative of the first times the second plus the derivative of the second times the first. Now I'm just going to make some substitutions. So g prime of 4 equals 1/2 4 to the negative 1/2 times f of 4, which we know is 3, plus f prime of 4, which we know is -5, times the square root of 4, which we know is 2. So I'm going to simplify 4 to the 1/2, or 4 to the negative 1/2, so that's just 1/2. So 1/2 times 1/2 times 3 is 3/4, and -5 times 2 is 10, so 3/4 minus 10 is -9 1/4, which is -37/4. So that's part A. On the AP test, you can actually just leave it as 3/4 minus 10 if you don't have a calculator. Part B, quotient rule. So g prime of x in this case would be derivative of the top times the bottom minus the derivative of the bottom, which is just 1, times the top all over the bottom squared. So if I'm going to substitute in 4, I have f prime of 4, which is -5, times 4 for x, so I'm just going to replace that with -20, minus f of 4, so -3, all over 4 squared. So it's -23/16. Lastly, both of the following fail to be differentiable at x equals 0, but not for the same reason. Explain what's happening. So if I take the derivative, I have 4/5 x to the -1/5, and I have -1/3 x to the -2/3. So this is the same thing as 4/5 x to the 1/5. Sorry, this should be a y prime. This is -1/3 x to the 2/3. So what I end up having is I have 4/5 x to the 1/5 for part A. This is going to end up being a cusp of some kind, because there is only one spot where the derivative is 0, or the derivative doesn't exist because 0 is in the bottom. But notice the derivative is negative all of these spots. This is a graph of the derivative. And then the derivative is positive whenever I plug in a positive value of x. So that's going to be a cusp. And I'm sorry, this is the graph of the original function. So the graph of the derivative would be something where I have negative values and then it goes off to infinity, then positive values over here. This is the graph of y prime. Whereas this y prime is going to have always positive values in the denominator because I have this squared. So if I graph the original function, what I'm going to end up with is 3 minus a cubed root. So it's going to end up being something, cube root looks like this. So it's going to be something that looks something like that, where I have a vertical tangent line at 0. And my derivative graph is going to be always negative, having a vertical tangent line at 0. Sorry, really bad at drawing, but at 0. And then it ends up leveling off as I go a little bit further along. And actually 3 minus that, I didn't graph that very well. That should actually be up 3. But the derivative is basically what it's supposed to be.